Hola. Me llamo Sara, pero no hablo español muy bien, así que voy a hacer mi presentación en inglés. Lo siento. Pero primero, quiero decir muchas gracias a Sebastián y los otros organizadores. Esta palabra es difícil. Por invitarme a esta conferencia. También muchas gracias a ustedes por escucharme. Me alegro de estar aquí en Colombia. I took Spanish in high school, and I practiced that a lot. So thank you very much for having me. I'm very happy to be here. I am keenly aware that I am the only thing between you and food right now. So I'll try and make it worth your while. As Sebastian said, this is me. I'm the chief consultant at DevMind. I'm one of the founders of Railsbridge and one of the directors of Ruby Central. I'm from San Francisco. This picture was taken pretty close to my house. And I know it looks lovely, but a much more typical photograph from that same location looks more like this. We do get a lot of fog. So it's very nice on the 2 or 3 days a year that it looks like that other picture. I do have a bunch of fancy titles and stuff at this point, but I'm still a developer. Most of my work is project work. I do consulting, and most of it has a lot of Ruby and JavaScript, front end and back end, I think like most of us these days. And when people say they do consulting, there's a lot of different things that they can mean. So to be more specific, what I mean is that I work with teams that are managing large code bases that have become unwieldy and hard to change, right? This is actually a pretty common problem right now among developers of all different technologies. And most people discussing them right now are calling them monoliths, which I think that's a reasonable name. And I see it in Ruby and JavaScript code bases, but I've also seen it from people that do other languages like PHP, CSS, Python, C#, Java. I went to a .NET conference last year. And the last two are really interesting because those two languages are strongly typed, which is a language feature that some people say leads to better software design. But it turns out you can make a mess in any language you want. And if this were a dynamic language problem, we wouldn't have these papers from the 70s from IBM about their big code bases that they're having trouble with. But where dynamic languages do come into play is the fact that this topic is once again at the forefront of our collective developer consciousness right now. And why is that? Well, one theory is that code is easier to write than it used to be. There's an explosion of dynamic languages in the last 10 years, also new frameworks in the compiled languages, though, and the addition of usable functional languages, which is pretty exciting. In other words, with modern technology, you can achieve a large, unwieldy code base faster than ever before, perhaps even when you're still a small company. You don't need to be the size of IBM anymore to have their code base problems. Because software is easier to write, our generation of developers is hitting this problem much sooner than previous generations of developers did. This is both good and bad, right? There are some people who say this is an unmitigated disaster, that all of these code bases represent failures on the part of the teams who built them. I don't agree. Some people say, well, you should have planned better. But a big, unwieldy code base that's hard to change doesn't necessarily mean that the team failed at planning. Code that's hard to change is built up technical debt, meaning they chose faster feature development today at the expense of code that's harder to work with later. And I think everyone in this room has made a decision about code that was definitely the right idea in the short term, but perhaps was not in the long-term interest of the code base, including me, many times. Ice cream is always a good idea. Right now, it is always a good idea. Even if it's 10 in the morning, it's always a good idea. But if you keep doing that, your body will wind to a halt. Now, that's easy for me to say, standing up here, right? Don't do that. You'll find a lot of blog posts saying real engineers don't do the expedient thing, or that you should treat your software like a craft and always take the time to do what's in the long-term interest of the code base. I look at it differently because I think of the right thing to do in a context that's larger than just the development team and the programmers. I think of the right thing in a context that includes them, but also the business around me, the marketplace, our customers, not just the code base and the dev team. Is that better? No? Yes. Sorry about that. These microphones don't tend to work very well with people with glasses, is one of the things I've noticed. So please wave at me when I need to do that again, because I'm sure I will. So sometimes incurring technical debt pays off. Some teams do it deliberately as a strategy to move faster, particularly in the early days of a company. And their competitors that put structures in place to support a large code base can't iterate as quickly. Sometimes technical debt buys you your company's continued existence. And so the code bases that have these problems are the ones that have been successful, that are making money. So we should all be so lucky to have those problems. But once you've survived, whether you survived to a new funding round or you survived the tenure of a developer who seemed more senior than they were, then you have to do something to get rid of that debt, because working in these code bases currently is not very much fun. But the vast majority of us work on these. And programming is supposed to be fun. That is my theory. So we need to make working in these large legacy code bases fun again. Now, recently, I've seen a lot of teams attempt this maneuver with microservices. That rant is another talk entirely. But I will say that many of those teams end up doing something like this. The main reason I like microservices is that I feel like my method calls are too fast, and I would prefer to throw in some latency. Carving services out of a monolith and carving objects out of a large class are the same skill. And if you haven't been doing good object design in your main code base, then you don't yet know what the large-scale abstractions are that you need. You have a guess, but you'll be wrong. That's part of the deal. When you're wrong in a single code base, all you have to do is adjust the object boundaries. When you're wrong in a services cluster, and you have to adjust service boundaries, that is a much more expensive way to learn. So before making microservices or doing a rewrite, you have to get better at object-oriented design. And I don't mean the top-down figuring everything out in advance type of design. Anyone can make up one of those diagrams, and it's usually about as correct as the first set of services that you design, which is to say not very correct at all. The better thing to do is to learn how to refactor your way into good design. Learn how to read the signs your code is telling you and make the changes that move you towards cleaner code over time. If you don't develop that skill, you'll just end up with the same mess you have now, but in different packaging. This is a joke account, but this is actually a pretty real situation. Refactoring your way to good design is not as shiny as microservices, but from a cost perspective, it's more responsible. Plus, you can still find and replace. That's pretty awesome. So we started seeing a resurgence of interest in object-oriented design, particularly in communities like ours that weren't particularly interested in it a few years ago. And there's now lots of books and blog posts and conference talks about software design. I'm sure you all are familiar with this lady. If not, you will be so after lunch. This is the best of the modern takes on object design, in my opinion. And I love this book, and I love all the blog posts, and I like reading about these things. But I had a problem, which was that what I do in my client work doesn't really look anything like this. The books and the talks and everything, they use example code being written from scratch to tell you how to put the right boundaries around your objects. But going into a big, messy, monolithic code base where no one heeded anyone's advice for years sometimes, going in there and moving things around doesn't seem a lot like that. It doesn't seem like object-oriented design necessarily. For a long time, I called it refactoring. Turns out, though, that software design and refactoring are not separate ideas. I know it seems a little odd. Let's define some terms. Talking about software design, I'm not talking about architecture or systems. I know Nicholas said earlier that a modern application is really a constellation of applications working together. But when I say application, what I'm talking about is a single code base. And within a single code base, software design really is nothing more or less, I suppose, than deciding how your code is arranged. And many people think that software design is something completely separate from programming. But in reality, when you're programming, even if you're not consciously making any decisions, you're still doing design. Every time you put a method in this class and not that one, you're doing design. And you can try and do it ahead of time. Some people do. But the vast majority of software design done by developers in our industry is inline. Just like programming, you'll be bad at it at first, and you get better at it the more you practice. So specifically, object-oriented design, grouping related functionality in objects. This does not sound anything like the Wikipedia definition of object-oriented design, which is this: planning a system of interacting objects for the purpose of solving a software problem. There is nothing in my definition about planning. And that's on purpose. Like I said before, talking about software design in general, I don't think of it as a planning activity. I think of it as something we do inline in the process of programming. Now, this is not a common definition of object-oriented design. I look at it as the difference between how it's taught, especially in school, and how it actually works on the ground. This definition fits how it's actually performed. So before we move on, let's talk about a few things object-oriented design is not. Object-oriented design is not a language feature. It's a way of thinking. You can write object-oriented code in CSS. You can write it in C, or JavaScript, or Java, or C# or Ruby. Languages that have explicit syntax support for objects are what you'll hear people call object-oriented languages, but that really just means languages in which it is more convenient to make objects than other languages. But that's a bit too long. So object-oriented design is just a way of thinking about code arrangement. In some languages, it's easier to express than others, but it is possible anywhere. You can buy me a beer and ask me about object design in Haskell sometime. Object-oriented code is not a destination. It's a means to an end. You don't write object-oriented code for its own sake, or because it's somehow morally or professionally better. Object-oriented design is not inherently better than any other way of arranging code. It's a means, it is a strategy that we use mindfully to move us towards some larger goal. And for most of us, that larger goal is ease of change. We build software for people who don't really know what they want. They imagine one thing, but they change their mind when they actually see it in action. Or the business shifts focus, or a key person is replaced, or it's Tuesday, right? The only constant in software development is that the end goal shifts as we build it. And it wouldn't do us any good to wait because the act of building is what causes it to shift. In theory, object-oriented design makes it easier to respond to shifting requirements. But I'll bet there are many people in this room that have been on a project where the code was parceled out into small objects, and that made it harder to respond to shifting requirements rather than easier. So to understand how that happens, and to see how we can avoid it, we have to take a step back and consider the goals that we have when we're designing software. So there's two useful axes to consider when we're looking at different ways to design software. On the bottom, we have the cost of understanding the big picture of your code, low or high. How hard is it to figure out what's going on? And on the side, we have the cost of changing the code, low or high. And every choice about how you arrange your code goes somewhere on this graph. So let's start with something besides objects. Let's start with procedures. So someone does a get on /calendar to see their calendar for the month, and a procedure is executed, a list of instructions. Determines the date range, fetches events within that range, draws the right shaped grid, places the dates on them, and returns that page to the user. It's pretty easy to understand what happens in a procedure. Cost of understanding is low. Everything that happens is right there in an ordered list in one place. The trade-off on a large project with lots of long procedures is that the cost of change is high. And the biggest devil in a code base like that is duplication, which forces you to make multiple changes in the code to make a single logical change. So procedures belong up here in the upper left. So some projects, having been burned by the high costs of change with procedures, go completely in the other direction. They make everything into a tiny object that doesn't do very much. In this kind of world, when you call a get on /calendar, a route receiver picks up the call, and then it creates a route resolver that looks up the URL and figures out that it needs a calendar route resolver, which it gets from the calendar route resolver factory. And then the calendar route resolver looks at what you're requesting and instantiates a get calendar index object, which sends your parameters to a calendar parameter manager, and so on from there. So the sequence of events in this world is not written down anywhere in the code. You just have to trace through it to figure it out. Little pieces of functionality spread across many classes. A system like this is harder to understand than a procedure. The cost of understanding is high, relatively speaking. A list of instructions will always be easier to understand than when the instructions are spread across a set of objects. However, once you understand the system, the cost of change is low. Assuming you've got the right abstractions, which is a notion we'll deal with in a moment, it's relatively easy to take, for example, one parameter handler out and put another parameter handler in. So a set of small objects goes down here in the lower right. So let's talk about code up in that upper right-hand corner. Code that has both a high cost of understanding and a high cost of change. This is the worst of both worlds. There are two types of code bases here, both of which are actually quite common. The first is a code base made up of really big objects. Maybe it's something like, I don't know, a Rails app that dictated an initial set of classes, and all behavior just sort of accreted onto those classes. Huge objects always seem to be the ones that are core to your application. They change in every commit. Changes go wrong easily, because all that functionality in one place means unintentional interference is going to happen. And the other type of code base that goes in this quadrant is small objects gone wrong. And this is what happens when you try and break down a big class but don't get the object boundaries quite right. And then it's both hard to understand because it's objects and hard to change because for one logical change, you still have to make changes in a bunch of different places. So the wrong set of small objects is kind of the worst case scenario. Right? Really big objects are bad. They're not that bad. So there's two questions here. The first is, can we get here? Is this a mythical place? Can this place exist? I'm not actually going to answer that question at all, because I'm much more interested in the other question, which is how do we move our big lumbering code bases out of here? It doesn't really matter where we go. Any direction will be an improvement. But usually when the code base is this size, reducing the cost of change is worth increasing the cost of comprehension, so people want to go down here. And so if you ask the internet how you take a code base from this quadrant to the other, they'll say things like solid and design patterns. How useful is solid exactly? Let's have a look. And then we'll look at some design patterns. Solid sounds really awesome, right? Who doesn't want solid code? To be a solid programmer, it sounds very attractive, I suppose. Yeah, it depends, I suppose. There are lots and lots and lots and lots of object-oriented principles out there. Academia has been studying object orientation for decades, and they really, really like to make up principles. However, academics tend not to deal in volumes of code. So a lot of the principles that they've come up with are quite academic. So in the 90s, Robert Martin took 5 principles that seemed most relevant to working software developers and assembled them into this acronym. So let's talk about what each letter means. So we'll be filling out this chart as we go. We have 3 columns, which is the name of the principle, the summary of what it means, not what it says, but what it means, and then a measure of how useful it is to actual developer life. So let's talk about S, solid, single responsibility principle. A class should have one responsibility, or to put it another way, one reason to change. And this was first articulated by Rebecca Worsbrock in the 80s. And this is a very fancy way of saying that smaller things are easier to understand and harder to mess up than larger ones. As far as utility goes, it's sort of in the middle. The difficulty here hinges on the definition of responsibility. If you've got a class that finds users, persists users, validates users, allows access to related objects of users, and contains business logic related to users, you could plausibly say that it's got one responsibility. It manages the user. However, you could equally plausibly say that all of those things are separate responsibilities and all belong in different classes. And the principle doesn't give you guidance because there is no universal right answer. Sometimes it makes sense to put all that together. Sometimes it doesn't. And that shifts over time, even within the same code base. As Sandy likes to say, and may say after lunch, the answer to every question in software development is it depends. So that's S. Let's move on to O. The open-close principle, this is usually stated as a class should be open to extension but closed to modification. Bertrand Meyer came up with this in the 80s. And this is a fancy way of saying that editing existing code is more difficult and more error-prone than just adding new code. So you should arrange your code base such that you can add new functionality just by writing new code without editing anything you already have. So that sounds great. It's really hard to imagine how it could actually work, at least in a code base of any significant size. It's not super practical day to day. So I put utility as low. So let's move on to L. L means Liskov substitution principle. This is perhaps the most academic of the solid principles. It's a very precise mathematical statement. Let theta x be a property provable about objects x of type T, then theta y should be true for objects y of type S, where S is a subtype of T. Yeah, right, great, okay. This is a fancy way of saying that anywhere you can use an instance of a class foo, you should be able to use an instance of class bar that subclasses foo, and nothing should go wrong. The Liskov substitution principle formulated by Barbara Liskov in 1987, when she was in her late 40s, by the way, so don't let anyone ever tell you you're too old to do something awesome. It basically says inheritance, that's a thing, we like that. Seems pretty obvious to us at this point, I think. But when it was first articulated, this was not actually necessarily obvious at all. And it was such a good idea that since it was introduced, we've baked it into our languages. It's now part of the air we breathe. We don't even notice it's there. It's had a huge impact on the way we write software, though, which is, I assume, why Martin chose to include it. Certainly not just because it started with L and he needed an L. However, while it's fundamental, it's not really a great source of practical help day to day. Utility is low. Let's do I. Interface segregation principle says that classes should only have to depend on the part of the interface they actually need. A fancy way of saying don't let changes to unrelated functionality in a class affect other things that use it. This doesn't make a whole lot of sense in Ruby. It makes a lot more sense in compiled languages. Let's take a quick look at why. Let's say you've got a class called musician that has 5 methods on it: record album, edit song, mix song, play set list, sell merch. 2 classes use this class, album creator and gig. They use different sets of methods that are not related to each other. And then you add another method called drive the van that's only used by gig. So you'd expect at this point in a compiled language that musician and gig would have to be recompiled, right? However, it turns out that all of the consumers have to be recompiled, even album creator, which didn't change at all. And so with just 2 consumers, who cares, right? But when musician has hundreds of consumers that have to be recompiled anytime you make any change to any of them, you can see how it's a huge pain. It makes rerunning a test, for one thing, a very long process. So to fix this, interface segregation suggests you break musician into 2 classes, studio session and tour, and then when a new method is added to tour, the album creator doesn't need recompiling. So that's cool. Dynamic languages don't really have this problem. The worst that has to happen is a reload, which is a lot faster than most compilation processes would be. Interface segregation does have one really useful core idea, though, and that is that if consumers of a class use non-overlapping sets of methods, that's a sign that the class has multiple responsibilities. Right? Remember S, single responsibility, and how we really didn't know how to define the granularity of the responsibilities that we wanted? Interface segregation is one of the ones that gives us a clue. So I put its utility high relative to the other ones. So OK, finally D, dependency inversion principle. Not dependency injection, although that is an implementation of the principle. Dependency inversion says depend on abstractions rather than concretions, which is a fancy way of saying that if you want to make a new thing, a new instance of a class inside another class, like here we're making a new instructor, think about creating it outside and passing it in instead. This has the effect of moving all of the choices you're making towards the edges of your system. And there's lots of dependency injection frameworks out there. Angular is a dependency injection framework, or has a dependency injection framework, as does .NET and Java. They make it easier to test classes in theory. Many of them have become essentially gigantic global state. So it's sometimes a bit difficult to tie it back to the principle, but it does seem to be something that a lot of people see in theory, so I put its utility high. So now that we've filled it in, let's look at this chart for a moment. Solid has principles of vastly varying degrees of utility, or concreteness. The other end of that spectrum is abstraction, right, which describes a general rule that sounds like a good idea. We all can agree on it, but it's hard to connect it to code you're looking at in your editor. And none of these, not even the ones rated high, not even the I or D, seem like they're useful day-to-day for refactoring code. I mean, it's nice to say make the API on an object small. But on most of our projects, that ship has sailed. And we just got to figure out what to do now. So we need things that are more concrete to guide what we do every day. It's not clear how to find them. What about design patterns? Maybe design patterns are what we're looking for instead of design principles. A design pattern is an example set of object boundaries that seem to work well in many situations. I'll give you an example of a pattern called the observer. Let's say you have a user class, and when a new user is created, meaning someone has signed up for your service, it automatically sends them an email to get them to confirm their account. Normally, this is fine. If your class is small, your object graph is uncomplicated, it's totally fine to leave that there. But a lot of times, user gets to be one of the biggest classes in your system, and it can be annoying to have it send email automatically every time you want to make one. And so you're looking for ways to find it to turn it off when you're creating a user in your test. Every test requires you to create a user. So you want to separate user creation from email sending so that it's easier to turn off. So you make a new class called user observer. You move the email functionality over there. You give it a nice set of creepy googly eyes so that it can observe the user class. And now when a new user is created, the user observer notices, and it sends the email. So that's cool, right? You've reduced the class of the size of your user class. You've made it easier to turn off email by just deactivating the observer. You've made the code easier to change by separating these responsibilities. However, you've also made it harder to understand. You used to only have one place to look to see everything that happened when a user was created. Now, it all happened in the user class. Now you have two places to look. Because it's a separate class, other people may not know it exists, let alone that they have to turn it off. And then may be unpleasantly surprised when the users they create get email. If your code starts out here and you apply the observer pattern as we just talked about, you've moved your code down here. You've made it easier to change, which is great, but you've made it harder to understand. Most people read about patterns and then they start looking for opportunities to apply them. And they assume that making less structured code into patterns is always a good idea, but it's not. Patterns are not a universal good. Nothing is free. Everything has a cost. And that's the hard part. At what point does the lower cost of change outweigh the higher cost of understanding? That's not a question with a single answer. It'll be different at different parts of your code. It'll be different at different times in the same part of your code. So patterns give us much more concrete ideas about how to break up code, but they don't really tell us anything about when. So we're still missing something. We need one more thing to help us figure out what to do with the code that we have. So here's an idea that I found useful when I was thinking about this. Strategy and tactics are military concepts. I did not grow up in a military family, so for most of my life, I thought these two words meant exactly the same thing. Turns out they don't. A strategy is a high-level objective that will move us closer to some goal, and a tactic is something you do on the ground to achieve that strategy. So let me give you a non-code example of how these work. Your goal is to be a pro mountaineer. Your strategy is to climb this mountain that few people have climbed before. And you're starting from the bottom, down here in the lower left, but you need to make it to the summit. There are no trails. You've got to figure your own way up. The strategy is where you want to be at the end of the day, at the top of the mountain. And your tactics are how you get there. Tactics include the planned route, the contingency plans. And they are guided by, maybe changed by, the strategy as you walk up the mountain. So you've got a bunch of possible routes you could take. You could walk along a tree line. You could go up this little rock face thing here. You could just go straight up. Whatever you want to do. And they all involve different tactics, walking versus climbing versus rappelling. And the actual route you take will depend on the weather, your skills, your gear, and many other things. Oh, there we go. Once you do choose a route, it's still probably not what's actually going to happen. If you get to the base of the ridge and discover that an avalanche has made it too perilous to go that way, you change tactics because your strategy of climbing the mountain is no longer in line with your original tactics. Part of your tactics include determining when to change them. But what would happen if all you had was a strategy? All you know is, OK, there's a mountain, I need to get to the top of it. If you set out to achieve this strategy without working out any of the little steps you take to get there, it's not really likely to work out very well. You may get to the top accidentally, but it's more likely that you'll find a few fruitless paths, and then you'll get yourself into a valley you can't get out of, and you'll have to signal to the park rangers to come airlift you out. So you need to have tactics, or you probably won't achieve that strategy. And so our actual goal clearly is not being a pro mountaineer. It's changeable code. That's the promise of objects. And one way to think about strategies and tactics for changeable code is that our strategy is object-oriented design, and our tactics would then be things like solid and patterns. And this is how object-oriented design is taught, particularly in academia. And this is how most developers look at it, whether or not they can articulate it. For most people, solid and patterns are the tactics we use to achieve object-oriented design. And there's a problem, though, with this picture of the world, and that is that object-oriented design isn't actually a strategy. Remember, a strategy describes what we want our world, or in this case, our code base, to look like at the end of the day. And object-oriented design doesn't really describe that. On the other hand, solid is reasonably good at describing what our code base should look like when it is quote unquote finished. Single responsibility principle, for example, would make a good strategy. Describes a state of our code base in which there is one responsibility at the right granularity per class. If we had that, our code base would be more changeable. All of these principles describe a code base utopia, if you will, where all you have to do is add new code to add features. These are all at some level descriptions of how you know your code is right. If your code were like this, it would be more changeable. And what that means is that they're a set of strategies. They're a great set of strategies, but we've been trying to use them as though they were tactics. You can't just apply the single responsibility principle directly to a 1,000-line class, right? A class like that has a muddy set of abstractions spread across multiple methods, each that are hard to distinguish. And when you squint at the class and envision how you'd break it up, you're probably going to be wrong. The abstractions are hard to see because if they weren't, you'd have done them already. So trying to just sort of eyeball a large class and make it into something that obeys a single responsibility principle is basically like trying to head towards a summit without planning a route ahead of time. But we do this a lot. I've done this. I've been on many teams where a class got too big, too frustrating, so we'd schedule a week to refactor it. And we spend that week just kind of looking at the class and trying to surface the right abstractions. I call these things stop the world refactorings. And I've decided that you shouldn't do them. But what's wrong with this, right? Refactoring is part of being a good software developer. So taking time to clean up and make code better is important. This is true. But two interesting things happen when you stop the world to refactor. The first is that the product team is really unhappy because you're taking a whole week off from their perspective, meaning you're not working on anything they can see. And the second thing is because you're time limited, you feel pressure at the end of the week to break that class up somehow, even if you're not entirely sure yet where the right boundaries are. And both of these are bad, right? Maintaining trust with your product team is one of the most important parts of your job. You can only tell them good software engineering practice so many times before they start wondering why, with all of this good software engineering practice, we aren't getting features done more quickly. And rushing through a refactor is exactly how you end up here. The only way to make a stop the world refactoring work is not to do it. It's like global thermonuclear war. The only winning move is not to play. So when we apply strategies as though they were tactics, we end up with these ham-handed, mostly unplanned, unpopular changes that more often than not just leave us in a worse place than before. We're doing this, and it's frustrating. One of the things I've been thinking about recently is why good developers that started out in object-oriented land are turning to functional programming. Certainly novelty is part of it, but there's a strong undercurrent that is fundamental criticism of objects. They say it just doesn't work. What they're actually saying is that there's a summit there and they can see it, and it seems like they should be able to get to it, but they can't. And what we're missing is a set of tactics that can get us up there in explicit small steps. We need things we can do every day as we're doing feature work to inline our refactoring over time and allow the right objects to emerge from the mess. Patterns are part of our tactics, but they're not everything we need. Right? Earlier we talked about the fact that patterns don't tell you when is the right time. And if we set off with only patterns as our tactic, it's like telling the mountaineer, okay, here's your tactics. You can climb an ice wall this way. You can scale a cliff that way. That's how you walk along a rock ledge. And all right, go. And there's definitely some skill involved in climbing an ice wall, but the real skill lies in knowing when to do it and when not to. When you come to an ice wall, should you climb it or should you look for a way around? When you see code you could change, should you change it? This is our missing piece. We have solid, we have patterns, now we need guidelines. I've got 6 of them for you. I made my own acronym. I figure if it worked for solid, it can work for me. Stable. This mountain is solid, which is cool. When I'm trying to go up it, though, what I really need is stability. And the same is true in my code base. I want to know that if I make a change in one part of the code, it won't cause an avalanche on the other side of the mountain, right? So let's go through these tactics. S, smell your code. Study code smells and the other don'ts so that you can start identifying things you could fix. Martin Fowler's refactoring book is great for this. I've worked with teams who would pick one code smell for lunch once a week and just talk about it, look for examples. You want to start noticing and naming the problems in your code you look at, even though you won't be fixing them all yet. Second is tiny problems first. In messy code, there will be lots of smells. They'll overlap, and they'll intertwine, and they'll interfere with each other. It will be hard to see what should be made with all of this mess. And the best way to get started is to pick a really, really small problem that you know how to solve in a very concrete way and just fix that. For example, just rename a variable whose usage has diverged from its name. And pick the smallest problem to fix, even though you see enough of the larger problems to start guessing at their answers. Your goal is to see the large problems better by clearing away the small problems that obscure them. The more information you gather about these larger problems, the more likely your eventual abstractions will be right. Proper abstractions are worth waiting for. Let them emerge from the code you have by clearing away the easy cruft. A is for augment your tests. You will almost certainly have to do this to be able to refactor large classes. You need integration tests one level higher than the class you're working on. And you need these in place before you start doing any other refactoring. For example, in a server-side MVC, if you want to refactor a big controller method, you'll need view-level integration tests in place that exercise it. If you want to refactor a big model, you'll need controller-level integration tests. And in general, test behavior rather than implementation. That's why you need to go one level up. You need tests that describe the behavior you want to keep, not the implementation that you know you don't. And this may mean getting rid of some lower down unit tests and or writing a new set of tests at a level you haven't had them before. So B stands for back up when it's useful. When the code has an abstraction in it that's no longer serving you well, sometimes the most useful thing to do is rewind the code into a more procedural state, put all the duplication back, and start over. It is much, much harder to move from a procedure to the right set of objects, it's much easier to move from a procedure to the right set of objects than it is to move from the wrong set to the right set. So don't get caught in the sunk cost fallacy, right? Don't forge ahead with a set of objects that don't fit now, let alone in the future. L is leave it better than you found it. During any one expedition into the code to add a feature or fix a bug, you won't be able to fix all the problems you see. Sometimes the only thing you have time to do alongside your stated goal is rename a method so it describes its behavior better. And it seems really small, right? Our instinct is to save up a bunch of those and do them all at once. But don't give into that stop the world temptation. Fix one thing. Fix the smallest thing when you're working on a story that concerns this code. I was a Girl Scout back in the day. I don't know if you guys have these down here, but we did a lot of camping and outdoorsy stuff. And our rules when we were out camping was that we always left a campsite in at least slightly better shape than we found it. We picked up one piece of trash that we didn't drop. And over time, this makes a better experience for everybody, including ourselves. If you change that one method name, you're removing a little piece of cognitive dissonance. And the next person to come through this code will be able to understand it more easily. Maybe the big abstraction will suddenly be obvious. I was a Girl Scout back in better shape than we found it. We picked up drop. And over if you change that one method name, you're removing I was a Girl Scout back in better shape than we found it. We picked up drop. And over if you change that one method name, you're removing I was a Girl Scout back in better shape than we found it. We picked up if you I was a Girl Scout back in better shape than we found it. We picked up